right. Yeah, welcome back to day 2 of our workshop. And so the first session will be all about benchmarking. We're very happy to have Joe Emerson here of the University of Waterloo and also Keysight Solutions. And he will tell us all about benchmarking and diagnosing errors. Please take it away.
Great. Thank you for the introduction, and thank you to the organizers for the opportunity to talk about this topic, which is near and dear to me. So I'll talk about benchmarking, which I construe to be somewhat different than diagnosing errors, and they're both very relevant. I think when it comes to benchmarking, we're talking about figures of merit or performance. When we're talking about diagnosing errors, we're talking about learning details of the error profile of the system, and this is increasingly relevant now. Finding scalable ways to do that, and that information flows up and flows down. So on the one hand, diagnosing errors is useful to the people doing the pulse design and the architecture of the system to understand how to reduce those errors. On the other hand, the information can flow up to inform, for example, decoder strategy and so on. So here's kind of the topics I'd like to cover. I decided to do a last-minute change to my slides and rearrange the order of some topics. So hopefully that I did the editing correctly. Otherwise, you might see me surprised by some slides and where they appear. In particular, I added this interlude to talk about randomized compiling because it's actually critical to understand it in the context of what do we want to diagnose, what do we want to benchmark. And so I'll give some mathematical background and some motivation, and then I'll talk about just a quick review of component level benchmarking, which is by now well understood and well established. Ideas around randomized benchmarking, some recent improvements on how to do that more efficiently, and then the randomized compiling interlude to talk about closing the gap between diagnosing errors using randomization methods and system performance, which normally would not have randomization, and that's where randomized compiling comes in. And then I'll talk about newer tools around benchmarking and diagnosing errors at scale. Both cycle benchmarking, which is the idea of understanding the performance of a multi-qubit system at one clock cycle, and then system level benchmarking, which is understanding a broader circuit performance. So I think it's important to remind everyone the word fault tolerance is a great marketing term because it kind of gives the impression that there will be no errors once we achieve fault-tolerant quantum computing. And that's simply not the case. Steve highlighted this in his talk, but it's important to realize that quantum error correction of fault-tolerant schemes correct a subset of the errors. Errors happen beyond that subset, and then you'll get faults and errors in your quantum computation at the logical level. So the problem of errors is here to stay. The problem of understanding errors will continue at the logical level, both at the logical components, logical cycles, and logical circuits. And I think it's worth emphasizing that because I think people tend to forget it. Another important topic, which hasn't, I think, really been embraced by the community completely, is this idea that once we, have large-scale systems, whether they're NISQ systems or fault-tolerant implemented logical circuits, we're going to try to run algorithms doing things like quantum chemistry. And there, the problem is we know there's going to be errors, and we have to understand the errors that are happening at the logical level or the NISQ level, because these aren't solutions we can check classically. So in other words, you're trying to measure, you're trying to simulate, say, the binding energy between a protein and a ligand, which is kind of one of the exciting things we hope to achieve with this field. And, the quantum computer does the calculation and spits out a solution that's, 0.1 millielectron volts. Well, how much can you trust that solution? How accurate is it? So we need tools to validate and assess the accuracy of these solutions at scale. Just kind of this naive notion that power of quantum computing grows exponentially, but the number of error parameters we have to worry about grows at least as 2 to the 4n. So it's even more dramatic growth. And of course, this 2 to the 4n number is just counting the parameters in a completely positive trace-preserving map. And errors do not fit into that paradigm, right? So we have non-Markovian effects. We have gate-dependent effects. The errors can depend on time and location of when the gate is applied. So the error complexity is an enormous challenge. I have a sneeze coming out. Okay. So just some mathematical tools. So the most commonly learned error model is probably this Krauss operator representation, which has this familiar form. And then there's also this chi-matrix representation where you choose an orthonormal basis of linear operators, and the information about the channel is contained in this 2 to the 2n by 2 to the 2n matrix chi. But I think these are not the best tools to work with to understand errors. My favorite tool is this so-called Liouville representation, which is a simple linear algebraic representation of what is a linear map. Ultimately, error processes in the completely positive map limit with assuming Markovianity is just a linear map. So why not represent our error processes, our quantum channels, as linear maps? And so we can do this by just remembering we have some mapping of density operators to density operators. We can expand the quantum state in terms of a basis of operators. We have this nice inner product structure to calculate the coefficients, and then we can construct this matrix via this inner product. And then we can calculate the output components of the density matrix using that matrix. And the most important part of this is that we have a natural composability structure. So matrices corresponding to channels happening sequentially in time just multiply like standard matrices in linear algebra. And so it emphasizes that we're just dealing with linear algebra, which means all the familiar tools of linear algebra immediately apply, diagonalization and so on, and the composability I mentioned. And then probably the most convenient map to choose, representation to choose, is choose your operator basis to be the Pauli basis. The familiar Pauli operators, which I've illustrated here. So the chi-matrix would look like that in the chi-matrix picture. But in the PTM representation that I just, in the Liouville representation, in the Pauli basis, we call this the Pauli transfer matrix, or PTM representation. And you have this very nice structure where the m and n coefficients correspond to non-unitality and trace preservation. So normally these are 0 in the limit of those two conditions being fulfilled. And more importantly, we have this nice rotation matrix in the bottom, which is just this row is one-dimensional and this column is one-dimensional. So that's 2 to the 2n minus 1 by 2 to the 2n minus 1. And that contains very interesting information, which has a natural classical interpretation for many error channels or quantum channels. So think about, as an example, a simple rotation about the z basis. And then that's the representation of the unitary matrix. And if we go to the superoperator representation, we get the representation of that in O3. So just the standard rotation in three-dimensional space that you learned about in second grade. And an important thing to notice, even though I'm just working this out here for the example of a Z rotation, is that for any unitary rotation, you're going to find that the off-diagonal terms for any unitary on any dimension, the off-diagonal terms are going to grow linearly with the error parameter, and the diagonal terms grow quadratically with the error parameter. So normally, if you have an identity channel, this is all ones on the diagonal and zeros everywhere else. So we want to do cos theta minus 1, which just gives us this theta squared term. So if theta describes the strength of your error, say to a miscalibration of your control, and if that error is 10 to the minus 2, then you're seeing it at the 10 to the minus 2 scale in the off-diagonal terms, but at the 10 to the minus 4 scale in diagonals. So somehow these diagonal errors are more benign. One of many reasons why we want to look at those errors in particular, those diagonal terms of the error model. Now think about what's called a stochastic error model. This is a favorite of fault-tolerant theorists, is to consider the errors are either depolarizing, which is a simple case of this, or a Pauli error channel. These are not physically realistic errors. But mathematically, they're very well defined. So we assume a probability distribution over possible Pauli errors. So in the chi-matrix picture, you would just have the diagonal terms. And it's important to realize that typical errors we see in the experimental setting, finite precision of control, drift, things like that, that leads to fundamentally coherent errors. Now, if these errors are fluctuating, if your control is fluctuating on a very rapid time scale, then that'll convert to a dephasing channel on the time scale of the snapshot you're looking at the system. And that would, of course, give you a stochastic error channel. But if they're fluctuating more slowly on the time scale of your gate, then you're going to have a coherent contribution. And that's what we see in typical experimental systems nowadays. If we think again about the PTM matrix, then we have this beautiful story where basically the probabilities of these Pauli operators in the PTM, in the stochastic error channel, just convert to eigenvalues of a diagonal PTM matrix. And the eigenvalues of the diagonal matrix have this very simple relationship to the probabilities you think about as physical. So these probabilities, like this is the probability of a Z error on qubit 2, an X error on qubit 3, and so on. And then we can compute the eigenvalues by just summing over the Paulis that commute and anti-commute with the Pauli of interest and summing over those probabilities. So this is very powerful once you realize that if you're lucky or if you are clever and have a Pauli error channel, then all of a sudden we can learn about the noise by exploring the eigenvalues of this matrix. So let me just, one more thing I want to talk about are figures of merit. A very common figure of merit is the average gate fidelity, which is you take your error channel, you act on a family of states, you average over all states in the Haar measure. It turns out you can also just average over any unitary 2 design or over a set of Cliffords and get the same thing. And then the common thing you hear about the infidelity of, say, a gate, when people talk about gates being 10 to the minus 2 precision and so on, it's just 1 minus that average gate fidelity. Also common figures of merit are things like the diamond norm, which is kind of a worst case error, and also the total variation distance, which looks at the output probability distribution and compares it to the ideal probability distribution for that process. And these will all come into play a bit later. All right, great. So that's a quick recap of some basics. And now let me just review kind of standard component level benchmarking and talk about just some very recent developments there. So the idea of randomized error estimation I think stems from this idea of saying, well, look, why don't we just run a long sequence of random gates? And as long as these gates are drawn from a group, and then we can talk about associating an error with each gate. And in the original result back in 2005, we just assumed the errors were independent of the gate and as a simple model. And then we showed you get an exponential decay where the decay parameter corresponds to the average gate infidelity. This is now just called the RB number. And there's some interesting literature on some gauge problem here, which I won't talk about. But ultimately, this is the intrinsic figure of merit people typically report for their performance. And a nice little thing people don't seem to realize is that the way this analysis works is that you can think about, as long as these gates are from a group, in particular unitary 2 design, then you could think about each random gate as a product of undoing the randomization of the previous step and then composing that with the next randomization. And so you can basically write this as a product of twirls. And that will, if you're twirling with the Clifford group, then you get a product of depolarizing channels, which is why you get this trivial decay, this exponential decay. So for 2 qubit gates, it would look something like this. And then more recently, there is a way of saying, well, suppose I'm not interested in the average error over a set of gates, but I want to know about the error of a particular gate. So my former PhD student, Iswar, and my former postdoc, Jay, developed this scheme called interleaved RB, where you apply some specific gate of interest, G, in between the random unitaries. And then you can interpolate what the error on that G was, that gate of interest. But it turns out that has problems because of a systematic uncertainty, which is rarely discussed in the literature. So a better way to do this is to use the cycle benchmarking trick, which instead of applying a random gate from SU4, whether it's a Clifford on 2 qubits or whatnot, you would just apply a random Pauli on each qubit. And then we call this the Baire gate you're trying to characterize. This is your MS gate or your C0 gate or your controlled or CZ. And then we call the Dress gate that gate with the single qubit randomizations next to it. And the reason for doing that is because if you do the analysis and look at the systematic error, so in other words, not just a statistical error, but there's a systematic error when you do these interleaved gates. And what you see here is a comparison of kind of standard IRB with the Clifford group in black, and the standard IRB with the SU4 group in gray, and then the cycle benchmarking with Pauli twirls. And what you see in blue is a much better statistical precision and a much better systematic bound. The systematic bound comes from the fact that you don't know if the coherence can cancel, can interfere constructively or destructively. And so strictly speaking, when you do IRB, and you claim, well, this is my gate error with, this is my gate with this uncertainty, you really have this upper bound, which people ignore. And so one of the reasons for encouraging people to do cycle benchmarking in this context is it reduces that systematic error and gives you better precision on the actual gate error, which is important for calibration. All right, that's enough about that kind of standard stuff. Now I want to talk about this way of closing the gap between randomized methods of error assessment and the actual performance of the system for a circuit, whether it's a fault-tolerant gadget or whether it's some NISC application, and how randomized compiling helps with that. So the idea of randomized compiling, before I show you the details, is to reduce a coherent error to a stochastic error. And there are many reasons why this is useful. One of these reasons is because if you typically want to talk about reaching the fault-tolerant threshold, you can't just compare the RB number to the theoretical threshold, because the theoretical threshold should be based on the diamond norm. But the diamond norm is upper bounded by this crazy factor, the square root of what you measure by randomized benchmarking. So if you get an error rate of 10 to the minus 4 by randomized benchmarking, the square root of that is 10 to the minus 2. So all of a sudden, you're losing 2 orders of magnitude and comparing the threshold. And then you also have this dimensional factor, which hurts for d equals 4. That's another factor of, whatever that is, square root of 4 times 5, square root of 20. And then if you're talking about the performance of your NISC circuit, for example, then you also care about the fact that the TVD is upper bounded by the diamond norm. And these both have the same scaling problem. You can show that the TVD also has the square root of R effect. So you want to get rid of that square root of R. And what you can show is that if your errors are stochastic, then the upper bound is linearly proportional to the error rate you measure via randomized benchmarking, because you've gotten rid of these terms of order theta in the off-diagonal. And so that's the beauty of this. And just here's an illustration of what the TVD means for people not familiar with it. All right, so this is what I told you already. The square root of R goes as theta, whereas R goes as theta squared. That's what you measure via randomized error estimation methods. And so this is the upshot of what you want to achieve. So what is randomized compiling and how does it work? The idea is you have some circuit that you want to implement, and then the squares just represent different single qubit gates. So we're going to break the system down into hard rounds or hard gates and easy gates. So hard gates are for example, the C-naughts, and easy gates are your single qubit gates. Later we'll see that we want the T gate, which is a single qubit gate, to be a hard gate, and I'll show that in a moment. But the idea is you apply random, say polys, for example, as the most common case, right before each hard gate. And then what you're going to do is you're going to push these single qubit gates through the hard gate and compute a correction. And then you for the next round, you do another round of twirling gates or randomizing gates, and then you apply the corrections. And then what you do is you compile everything together. So you get another circuit with a similar appearance as the original circuit, except you've basically rotated all of your single qubit gates, all of your easy gates, to something different. And then you average over these randomizations. And the result of that is to remove off-diagonal coherent terms of the noise. There's sometimes a small increase in circuit depth. If you have C-naught ladders, for example, you have to insert single qubit gates between the different C-naughts in the ladder. So that does add some depth to the circuit. But in many cases, that's not the case anyways. And unlike dynamical decoupling techniques, this does not require knowledge of what axis the noise is happening on. So to give you a little more details, here's kind of what it would look like technically. You start with your original circuit. You have some error associated with the single qubit gates. You have an error associated with the hard gate, the 2 qubit gate, and the T gate. And then you apply your randomization. You apply your correction gates, and then you compile everything together. And you get something like this after averaging over the randomizations. You get an effective stochastic noise model and your original circuit back once averaging over. So you get the same. And then an important, I keep seeing papers saying randomized compiling is also called polyframe randomization. So let's just be clear about this. Polyframe randomization was an idea put forward by Manny Nil in 2004. And he talked about just applying random polys and how this would work for Clifford circuits. But it's important to realize that randomized compiling works for universal circuits. And let me explain in detail how that works. And in particular, we're not just using random polys, we're actually applying a deformed twirl. So what we're doing is we're computing a correction gate based on the hard gate that's adjacent to the twirl. And by that way, we're compensating for the randomization on the fly locally as we go through the circuit. And that allows this method to work for universal circuits. So for example, the canonical example then is we take the easy gates to be Cliffords, which can be generated, for example, by the phase gate and the polys on 2 qubits, if we have 2-qubit gates in our system. And then we take the hard gates to be the Hadamard, the T gate, which is the square root of the phase gate, and some 2-qubit Clifford, like the CZ. And then the randomizing gates are just the polys. And in this way, we can run randomization. The PFR idea generalizes to universal circuits. And then here's just some old numerics, which we never published, just showing the idea. So if you imagine, you measure your infidelity using randomized benchmarking. Now, randomized benchmarking can't tell you if your errors are coherent or stochastic. It just tells you what the cumulative error is based on this effective depolarization. And now let's say you imagine, you numerically simulate that where some fraction of the infidelity you measured via randomized benchmarking is from stochastic errors. So if that fraction is 1, now blue is your original performance in terms of the TVD for some circuit on multi-qubits, and red is after applying randomized compiling. So the point is, if your errors are stochastic, randomized compiling helps you not at all for error suppression because your errors are already stochastic and it leaves them invariant. But if if the fraction of error is coherent, then you get a huge gain. And then, of course, that gain scales down as the fraction of your errors that are, say, dephasing, based on the time scale of your fluctuations, increases. So that's kind of a quick illustration. The other thing that's important to realize is the power of the Hoeffding inequality, which is the number of randomizations you need. Remember, you're averaging over these randomized circuits. The number of randomizations is independent of the system size and the circuit size. So number of qubits and circuit depth is irrelevant. All that matters is essentially you're bounding random variables which are bounded between 1 and -1. And so you get a very quick convergence to the optimum. So in this case, the best noise reduction is around 0.45. And here we reach that in about 15 to 20 randomizations. So it's a constant overhead. And now this, the one challenge for modern systems, contemporary systems, is you have to load a new circuit into the FPGA. So reloading the FPGA with a new circuit is a bit of an expensive thing. It leads to a delay. For some systems, like super qubit systems, it's much slower than the timescale in which you can run a shot. And so there is an overhead in terms of the total time due to that FPGA reloading limitation for a new circuit. But that's an engineering challenge that I think can be overcome. Here's some experimental data on the system here down the street here from Irfan Siddiqui's lab. This is a paper we published with them showing the use of randomized compiling. And in this data in particular, it's randomized compiling on random circuits. So we often have people tell us randomized compiling doesn't help with random circuits. Well, if you're running a fixed random circuit, then yes, it does. It reduces the error because it's getting rid of the coherence in that random circuit. Here's some nice numerical results that are unpublished with my wife, Virginia Frey. We were looking at the quantum volume and showing how randomized compiling would help with quantum volume, which is, of course, a canonical random circuit. And this is the ideal circuit, which you use to compute these heavy output probabilities, which are highlighted with the dashed blue. And that tells you these are the kind of the heavy output bins. And then the native circuit, of course, is going to deviate from the ideal because of errors. And then when you run RC, this is the performance you get. So you get a reduction of these peaks and an elevation of the minima. And the important part of this story, and this is an open question for the audience. I mean, I don't understand why this is the case, but if you look at the original definition of how to do the figure of merit for these quantum volume circuits, they call it the heavy output mass. And randomized compiling does not help at all for the heavy output mass. So the heavy output mass says, you flag the heavy output bins, and then you count the amount of probability in those bins. But it turns out if you change the definition of the figure of merit and say, instead of just counting the mass in the tagged bins, what if I just say, what's my ability to identify the correct bins? So in other words, suppose my goal is to experimentally determine what are the bins that are above median by accumulating statistics. Well, it turns out then randomizing does help. So it helps you identify the correct heavy output bins from the experimental data due to this improvement in performance here. But it doesn't help increase the amount of mass in those, the probability mass in those bins. So I do not know why this is the case. But anyways, I've included just to emphasize that randomized compiling does reduce errors in random circuits, like quantum volume circuits. Okay, now we'll get to kind of latest and greatest benchmarking at scale for large systems. So first we'll talk about cycle level benchmarking. Here the idea is, remember, with randomized compiling, we're already imagining breaking down the circuit into a sequence of rounds defined by the easy gate set and the hard gate set. So again, the easy gate set would be local Cliffords, hard gate set would be 2-qubit Cliffords, and the T gate and the Hadamard would be in your hard gate round. And then you're randomizing the easy gates with the twirling set. And then the dress cycle consists of this composite product here. And so the goal is now to learn the errors across an n-qubit register for some parallel instruction set of this type. And so the idea of cycle benchmarking is you have your parallel instruction set. So this is some parallel set of C-naughts, T-gates, and Hadamards. And then you apply, essentially it's essentially randomized compiling applied in the context of diagnosing errors. And then what you're doing with these green state preparation circuits and measurement circuits is you're picking out individual input polys and pushing them through the circuit and then measuring whether you got that poly again at the end. Remember, the effect of randomized compiling is to create this diagonal matrix, this diagonal poly transfer matrix. So all we're doing is we're now just sampling the eigenvalues of that poly transfer matrix. So here's an example of doing it for a non-Clifford gate, where now what you have to do is the correction gate would have to include a 2-qubit gate. So in this way, if you have a non-Clifford 2-qubit gate that you want to characterize, you can do that as well via this scheme. And now the simplest application of cycle benchmarking is to look at the total process fidelity across an n-qubit register. And so here what we did to show how easy it is to implement this is, and this is data from way back in 2019, also unpublished. So the problem with, I created a startup back in 2017, and the problem with that was that we put a lot of our energy into creating code that implemented our ideas rather than publishing our ideas. So we kind of fell behind in terms of publishing to build tools. So this is, again, unpublished data where we ran cycle benchmarking on all of the 5-qubit machines available at IBM Q at the time. And remember, there's some fixed connectivity. And so this is all possible 2-qubit gates based on the connectivity in this T-style shape of qubits, this T-shaped architecture. And in the last two columns, we're looking at parallel 2-qubit gates that were only 2 sets allowed. And then we measured the total process infidelity of each of these chips for each of these different parallel instruction sets. And just quickly summarized all of the capabilities of the system, and notice that you can see which systems are good versus bad, which 2-qubit gate combinations are good versus bad, and in a very quick scan. And some of this data is bad because there are various challenges with experimental systems. But one more thing I wanted to say about this is and again, just to emphasize what I mentioned, mathematically what's going on is we're inputting a poly into this effective diagonal channel. And remember that in randomized compiling, we're looking at an actual application with different 2-qubit gate combinations. But in the context of cycle benchmarking, we're fixing a parallel instruction set. We want to understand the errors of this parallel instruction set. So we repeat it m times to amplify the noise, as in randomized benchmarking. And so that's what's happening here. And the point is then these eigenvalues get multiplied, get exponentiated m times. And so we're measuring, say, if you put in the second poly, you're measuring the second eigenvalue. And this idea actually was put forward in the context of error channels back in 2007 in some very early work, but it wasn't until Joel joined my group in the mid-2010s that we figured out how to effectively create an error channel associated with some parallel instruction set via this randomized compiling trick. And so these two results combined gave what finally we summarized all of this in this recent paper that my former student Arnaud wrote up for us just last year. Now you can go beyond just measuring the process infidelity of each of these cycles and actually reconstruct the details of the eigenvalues. You can measure the eigenvalues and therefore measure the poly probabilities, which then all of a sudden tells you a lot of things. It tells you about what's going wrong in your system, how much crosstalk do you have, how good is your decoder going to work based on this information, and so on. And so here, remember, we prepare a poly, and now in the context of estimating the process infidelity, what you're doing is sampling uniformly from the possible polys. But now when you want to learn about specific eigenvalues and specific error probabilities, what you want to do is prepare a particular poly and study that. Particularly, you want to study the low weight polys and then estimate their fidelities. We call these the poly infidelities. So now an interesting thing is, of course, there's an exponential number of these eigenvalues. So you can't measure them all on a large scale system. But an idea that we proposed way back was that, well, if you measure the low weight errors, these are polys where there's lots of identities in the string, so weight 1 poly, weight 2 polys, then those can be sufficient to infer the higher weight errors if you assume that there's some correlation cutoff in the noise. So if you say error correlations only extend up to weight 4 in my system, then you only need to measure the polys up to Hamming weight 4, and then you can assume independence of the noise to infer the higher weight polys. There are tricks, for example, the method that Robin Harper from UCID with Wallman and Flamia and others has looked at Clifford twirling instead of poly twirling. But there was one important reason to use poly randomization instead of Clifford randomization in this context, which is that the error profiles you learn about now all of a sudden match the error profiles when you run that parallel instruction set in the context of a circuit. So that might be some gadget you're using for error correction, or it might be some parallel instruction set as part of your NISC application. So remember, local Clifford twirling does not work for randomized compiling because you can't contain the error. The entanglement spreads across the whole system and you can't track it. You can only undo the polyframe randomization promotes to randomized compiling only under certain conditions, and the standard condition for universality is use poly randomization, although there are others. There are some degeneracies in the reconstructed profile, which I won't talk about. But here's some data, again unpublished, we did in collaboration with Innsbruck in 2018, where we reconstructed the poly errors of their two different gate sets. So first we looked at just parallel single qubit gates on their ion trap with 4 qubits. And then what I mean about the Hamming weight is, so these are weight 1 errors, and then we measured the probabilities of all these weight 1 errors, and then we looked at the 2-body errors and reconstructed these probabilities, 3-body errors, and so on. And then what you're seeing here is a nice thing, which is that what you don't want for error correction is lots of high weight errors. So here we're showing that the 4-body correlations are quite small in probability mass compared to the weight 1 errors. I really wish we had published this data, but we didn't. And then we looked at the MS gate, which is a Clifford 2-qubit gate, and again reconstructed the same thing. And then we actually see many four-body errors because we're doing essentially 2-qubit gates in parallel on the system. And so yeah. Anyway, so we did that experiment, and then I think there's a lot of work required to kind of understand what this data tells you about your system and what error correction strategy and decoding strategy you want to use. I think in the interests of time, I'll just skip talking about these heat maps because they're hard to unpack. but it's just another way to visualize this data that's distinct from this method of just reconstructing a histogram. Let me skip that. Now, system level benchmarking is the final section of the talk. So we talked about benchmarking components. We talked about benchmarking parallel instruction sets or cycles. Now, what about benchmarking entire applications, entire circuits? How do we do that? So we've seen proposals for system level benchmarks. There's actually a whole zoo of system level benchmarks that have come out in the past few years. So several randomized benchmarks like quantum volume do not scale. It's important to understand that several aspects of quantum volume just don't scale beyond 40 qubits or so. And so that's exactly in the uninteresting regime. And we're interested in benchmarking performance at the scale of hundreds of qubits and thousands of qubits. So we want system level benchmarks that scale up. Then we've seen application suites proposed by QEDC and others. These also are idiosyncratic. Either they don't scale, there's something about the particular application in the suite that doesn't work unless you know what the solution is, or if you have or you need a small system. And there's several other problems which I won't get into, such as lack of distinction between error mitigation techniques that kind of exaggerate system performance and intrinsic system performance, which I think is important to always distinguish those things if we're trying to understand system performance. So what I'll talk about today is a method which I think solves all of these problems, which I call circuit benchmarking. This is again unpublished, but I've been talking about it since 2019, and the idea has not quite taken off yet, so hopefully it will soon. But let's talk about a recent paper by Quantinuum that came out just last week. So first, let me get to this. So, the best methods for component and cycle level benchmarking uses randomization techniques. In actual implementations, we see that dominant errors are control errors, which are these off-diagonal terms, which kind of are suppressed and not observed through randomized methods. And in particular, what Quantinuum did, which I think Quantinuum does a great job of benchmarking transparently, is they looked at the logical QFT, 3 logically encoded qubits, performing a QFT at the logical level on that. And they benchmarked all of their individual components, and then they also benchmarked the total performance, and they found a big gap between what they expected to get from performance from the logical level behavior and the actual system level performance they received. They used what are called average state fidelities for technical reasons, and they expected a performance around 0.9 based on the component performance, but they only got 0.78 in one method and 0.66 by another method of implementing this QFT. So you see there's this pretty big gap in the fidelity, and the question is, why is that? And they talk about different ideas about why that is in the paper, and maybe those are true, but for me, this is not surprising because they didn't apply randomization to the implementation. So their benchmarking methods suppressed coherent errors, and their implementation was exposed to coherent errors. And so this is my best guess, is that they didn't apply randomization at the logical level to close the gap between the system level performance and the benchmarked components. So let me explain this idea, which I'm hoping to convince some experimental groups to implement. But the idea is, and this is a result from my paper with Arnaud several years ago, is that if you look at the fidelity, so this, Arnaud likes the notation capital Phi for fidelity. So if you look at the process fidelity of an individual parallel instruction set, and then you want to talk about the process fidelity of some circuit implementing those instruction sets, then it turns out under some fairly mild assumptions on the noise, which I'll refer you to the paper because they're very technical, but basically the noise is well behaved. It turns out that the composite fidelity can be inferred from the fidelities of the parallel instruction sets used to make up that circuit. So here you have some dimensional factors which are order 1, and this squiggly line means it's an approximation, and the accuracy of this approximation is order R squared. So if your total circuit has order R as your infidelity of the circuit, is order R squared, then this is a good approximation. So now for this all to hang together, you need to use the same twirling group. So you measure these quantities, the fidelities of the individual layers or cycles you're measuring via cycle benchmarking. So if you use the same twirling group under cycle benchmarking, namely the poly group as the best example, then because now you can use the poly group to do randomized compiling on the circuit level, then you can now estimate the whole circuit fidelity from these component fidelities. Now this is awesome because first of all, if we could convince some of these cloud quantum computers to just publish their process fidelities for the exposed parallel instruction sets, then you can immediately say how pretty much any circuit you're going to run on that system is going to perform using this technique if you implement that circuit with randomized compiling. So that's pretty awesome. Maybe not great for business because you would mean that there's a lot less need to run actual circuits because you can infer how the circuit will perform just if this data is exposed. You know, people have looked at trying to do this with randomized benchmarking numbers, which various providers do provide on their websites. But you know, it's well known that that almost never predicts system level performance for all of the reasons I've talked about. But this is a scheme that would account for crosstalk, it will suppress coherent errors, and you should get a very good system level prediction from these cycle benchmarking numbers. And no one's done this yet, so I'm open to any experimentalists that want to collaborate on this. I think this would be a lot of fun. Now, the key constraint is this order R squared accuracy of this approximation. And the question is, how good is that? And so this is one of the reasons why I think this would work best at the logical level. Because at the logical level, we expect much more reduced errors. And so then you can do long depth circuits and this approximation will still hold to high accuracy. Notice that we can use this to talk about now figure of merit performance. I won't take this call, I just want to shut it off. Okay, so this is for applications for logical QFT or whatever. What am I doing on time? 5 minutes. But what's interesting to me also is that this can define a very nice system level benchmark that we can use to assess performance as we scale up systems and compare them. So here's an illustration of the idea. This is data taken, I think in 2020, again unpublished, on the IBM systems. And we just said, look, let's suppose that what we did is we took the data that I showed on a previous slide, where we looked at the process infidelity for all of the exposed parallel instruction sets on their 5-qubit chips. And then we said, now let's look at just random sequences of those parallel instruction sets, and let's just tabulate the fidelities based on the cycle benchmarking data. And then you can see, for example, the difference in performance between, say, the London chip and the Burlington chip. And if you have some threshold, say for my application to be interesting, I need the total fidelity to be less than 0.4. So this then tells you, okay, well, here are the chips that can deliver a total fidelity of 0.4 at these different circuit depths. So again, this is the idea of a lookup table that would tell you how the system will perform, that accounts for crosstalk, it accounts for suppressing coherent errors at the implementation level. One more idea in this family of ideas is instead of just talking about the fidelity of that composite circuit, we can also talk about the accuracy of some observable. So we can actually bound the total variation distance between the true probability distribution and the experimentally achievable probability distribution. I talked about this earlier. That's upper bounded by the diamond norm, which is actually just equal to the process fidelity of that circuit. Now, the process fidelity of that circuit is what we approximated via the product of the process fidelities of the cycles. So now all of a sudden we have a bound on the probabilities of different bit strings coming out of that noisy quantum computer and how close they are to the true probabilities. And now what we can use this in turn is we can use that this TVD bound to bound how close some observable will be. So you have say you're simulating an Ising model, you want to talk about the total polarization or total magnetization of that Ising model. Well, it's very easy to see that this gives a very tight bound on the total magnetization based on this table of process infidelities. I think I hear, oh, and now let's talk about a scalable quantum volume. So now the quantum volume is a well-defined family of randomized random circuits. Now, instead of, forget about heavy output and all that, let's just say, okay, well, let's look at the different random layers in my quantum volume circuit family. Let's measure those process infidelities. And then let's just talk about, well, what's the fidelity obtained by this product? And then that define a threshold for that, say, 0.66. And now that's a fully scalable benchmark for random circuits that applies across architectures, that applies, in arbitrarily large numbers of qubits. And again, we have this bound on the TVD. You could also apply the threshold on that. I mean, there's a lot of ways to do this. And then an open question I have is, we could probably actually bound the heavy output probability from this TVD. I haven't had a chance to look into this, but I don't know if we would even want to. I feel like the heavy output probability, maybe someone can explain this to me, but it's kind of an ad hoc figure of merit anyways. So I don't know why we want to bend over backwards to bound it. Maybe it's just best just to stick to these more primitive quantities in that context. And with that, I end my talk. So thank you for your attention.
All right. Are there questions?
Thank you for a fairly comprehensive talk. I have a question that I'm sure you've been asked before, but when you're doing randomized compiling, you're adding, let's say, in an n qubit system, you have, and depth m, you have like order n times m extra gates because you're adding a gate for every qubit and every layer. So these gates would also have errors, right? So how do you make sure that the amount of error doesn't increase with all the additional gates you need for averaging over these circuits?
Okay, that's a great question. There's a few answers. So let me unpack the answers to that. So first, let me talk about, are you really adding in those single qubit gates? So let me just pull up an example from the figure. There we go. So this is your original circuit, right? So you already have a bunch of single qubit gates. So you're not adding. In this example, there's no extra single qubit gates. There's no extra depth. There's a version of randomized compiling which we call local randomized compiling, which again we haven't, I think, published, but this was in the software from 2018 or something. But the idea is you could just do randomization around the 2 qubit gate. So you could leave these qubits alone, these idling qubits or these qubits subject. So you can just do, now that you only want to do that if you're confident there's no crosstalk. Because if you randomize on the idle qubit next to this 2 qubit gate, then you're going to reduce the coherence of the crosstalk, which actually ends up having a big effect when there's crosstalk. Now, as we see superconducting qubit systems switch, so IBM's switching from the cross resonance gate to tunable coupling, then you see a reduction in crosstalk. The tunable coupling, which Google has been using for a long time, tends to have reduced crosstalk. But every time we see a change in the architecture, for example, with ion traps, whether you have significant crosstalk on the idle qubits or not, seems to change by the month, depending on how they're designing their gates. So whether or not you want to do this, you do some preliminary experiments to see. But so in this particular example, you're not adding circuit depth, and you're not really, maybe you're adding an extra single qubit gate here. In the old case of the cross resonance gate, if people want to do a C0 or a CZ, they actually had to map that to their cross resonance gate via local qubits, it's locally equivalent to the C0. So when you think about a C0 ladder that you see in some of these VQE algorithms, right? So you do a C0 in qubits 1 and 2, a C0 in qubit 2 and 3, and so on, with no single qubit gates between them, then it looks like for randomized compiling, you have to insert single qubit gates there to achieve the benefit. So that does add depth, like you're saying. So whether or not you're adding depth or not depends on the structure of the circuit. But in the case of the cross resonance gate, you had to put single qubit gates to convert that to a C0 anyways. So hidden to the user is the fact that there were single qubit gates being inserted. So even though it looked like you had to add single qubit gates, you actually don't. But again, it depends on the details of the architecture, what native gates are exposed, and so on. Lastly, to answer your second part of your question, randomized compiling works well in the limit that the single qubit gates are an order of magnitude better than the 2 qubit gates. If you're in a regime where single qubit gates are as bad as your 2 qubit gates, then randomized compiling is not going to help much. One exception to that, the Hadamard and the T-gate are considered hard gates. So now T-gates are going to basically suck because you need these big overheads to create T-gates in these standard fault-tolerant architectures, right? So your T-gates, you're going to want to minimize that overhead, which means you're going to have very noisy T-gates, which fits perfectly within this paradigm because the T-gates are considered hard gates. So then again, you're going to hopefully your single qubit gates, which are basically more or less your polys and your phase gate, would hopefully be implemented with high precision, and then you get the best benefit.
Hi, thank you for your talk. I have a question regarding the cycle benchmarking. So if I understand correctly, you basically interleave the application of some gate that you want to understand with a random polygates. Mm-hmm. And at the end, you undo this. I can see how this is easy if you have a Clifford gate, because then every poly just passes mm-hmm. through, and then it's very easy to compute at the end. But if you don't have a Clifford gate that you're trying to benchmark, then I think every time you choose a random twirling operators, you'll find a different circuit at the end, which might be hard to compute and also hard to implement. So my question is this the case? Do you have any tips for dealing with this?
Yeah, no, that's, again, a very good question. And you know, the scheme does not, there are some issues with the scheme with non-Clifford gates. I mean, it works in principle. You're applying your randomization, and then there's going to be a residual entanglement created for a non-Clifford gate. And that's why your correction gate for the non-Clifford case spans the 2 qubits. Okay, because you have to undo, you need a 2 qubit correction to undo that entanglement. Now, typically with non-Cliffords, the problem is, oh, we can't, they're universal. They give us universality when combined with Cliffords. So with randomized compiling, for example, it's a problem because you can't now track the circuit anymore. But with cycle benchmarking, your entanglement never spreads beyond the 2 qubit gate. So it's easy to do a small 4x4 matrix computation to know what the correction gate is. So in the context of cycle benchmarking, it's actually easier to manage non-Clifford gates, 2 qubit non-Clifford gates, than in the context of randomized compiling. Another trick you can use is you can actually decompose that non-Clifford gate as a circuit made out of T gates and Clifford 2 qubit gates. And then you can just do randomized compiling on that kind of circuit fragment. So there are a couple of ways around it. How you do it depends on what you're trying to achieve. But yeah, it's a very good question.
All right, let's maybe take the other questions offline. Let's thank Joe again for the nice talk.
Great, thank you.
And we have another coffee break now, and then we will reconvene here. Thank you.